Hello class. Okay, so today I'm going to give a lecture finishing up our discussion on diodes. And let's start with our whole distribution. So you should be comfortable with this diagram now, where this is Pn0 and P of X does something like that. Okay? And where we're going to call this Pn for now. You know what it is now. It's Pn0 e to the e via Vf over kT. All right, but the reason why I'm doing that is because I want you to understand a simple way to come up with a diffusion current. So that you don't have to memorize the formula, because all you have to memorize is that J is E times the flux, so it's E minus sign times the diffusion coefficient times dP dx. Okay, and P of X is that formula involving the exponent and things like that. But the way I want you to remember it is that, and remember, we're evaluating this at x equals xn, that's what this is here. That's the edge of the depletion region. And I'm doing this because I want you to have sort of a way to remember how to do this, because this is an exponent, and so if you think about e to the minus x, right, the slope here is exactly this distance here, or this here, divided by L. So this is equal to, well, the minus sign goes away, ED times Pn minus Pn0 over L, the diffusion length. Right? Okay, and you can work that out taking the derivative if you want to, but this is sort of a way to remember it, that once you understand that you have this whole distribution there, and once you understand that the diffusion current, you're calculating this with the slope at the edge of the depletion region, which we'll talk about in a little bit, then dP dx is just dP dx P minus Pn0 over L. And so that's, pretty easy to remember. All right, and then we use our formula that Pn is Pn0 times e to the e Vf over kT. And we get that the whole diffusion current, we have to have the electron diffusion current, is, and so I'll put this in parentheses here, E, D, and I'll label it as holes. I'm going to go back and forth between the subscript being H and P, meaning for holes, but let me put holes here. So the diffusion coefficient for holes divided by the diffusion length for holes. And so that's this. And then Pn minus Pn0 is Pn0 e to the e Vf over kT minus 1, where this is that, where I've taken the Pn0 out. Okay, so go through that yourself, and that way you'll see that you can always derive this without really having to think about it too much. All right, now I have to add the electrons on the other side, and that's just writing down the same thing. E, D for electrons, and P0 over the diffusion length for electrons. And because this part is the same. because on this side, right, this is NP0 e to the EVF over KT, and it goes to NP0. Sorry. So what I've just done in the last few minutes was show you how, okay, any time of the night or day you wake up in the middle of the night and you say, oh, gee, I forget the formula for diffusion current in a diode. You can just draw the picture and reason it out and come up with the formula. Okay, so that's it, and you know, in principle, that's all you have to remember. We're going to do a little bit of manipulation on that to get it in a form that's a little bit more helpful. But first over here, I'm going to do a bit of a side, because you might have been wondering about something, which is that, okay, we reach our little thing here with P, you know, going like that. All right, so this is P of X. And what I said was, okay, the diffusion current is based on that slope there. And the slope is going down. So if you were to plot J, and I'll just write J there as a function of X. All right, remember this is Xn, the edge of the depletion region. What you will find, right, is that since J is the slope of this, that's also going down exponentially. All right. Now, so you remember back to your first electrical engineering class, right? What do they always tell you? Current can't go away, right? That's Kirchhoff's law or something like that, right? So what's going on here? J can't be changing. Well, what's happening is that there's another component here, so that the sum is the same. And this is the holes going from P to N, right, being injected by the forward bias. Now what's this component? Well, let's draw our diode here. All right. So here's our diode. Here's, you know, P and N, and here's X sub N, the edge of the depletion region. And so here's our holes, okay, and I'll draw it like that. Like there's basically this you know, big component of holes here. Can't draw very well. Being injected. Well, remember what diffusion current, what the whole premise behind it was that, okay, and what's going on here is that at any given point, right, there's holes disappearing. Okay, as P minus Pn0 over tau. And how are they disappearing? Through a recombination. All right, and what are they recombining with? From electrons coming from this side. Okay, so what's happening here, this is electrons moving toward the junction. And recombining, and those electrons, so basically, you know, every time a hole and an electron meet, they disappear, right? So the hole component is getting smaller, and the electron component is getting smaller too, right? Until finally, when you reach the junction, there's only the hole component. There's no recombination taking place at the junction itself. sometimes this is labeled the diffusion current and this is labeled the drift current, and you can see that the sum has to be a constant because every time a hole goes away, an electron has to go away too. So you could sort of draw this, you know, sort of better, but basically you just, I mean, maybe you can sit down and draw it if you want, but it's sort of easier to represent it by this plot here, that basically the holes, that diffusion current is going down exponentially, and it's being made up for by electron from the right, because remember this is n here, that are recombining with those holes such that the total, you know, J total is constant. So the point is, you don't need to worry about it, because this is the answer. Because at the junction, basically all those electrons are gone that came over from this side. And so all you have is the diffusion current. Okay, so, you know, I mean, that's one of those things that you may or may not want to care about because it's sort of explaining why the answer is simply what it is, and you know, it explains why you know, you take the slope there. Okay, so you know, that covers that part of it, and so we just get back to, you know, all we have to know again is that slope at xn, and so you can just reason it out and come up with the equation. Now we're just going to perform a little bit of manipulation to reveal a few things, and in order to perform that manipulation, we're going to substitute in for Pn0, which of course is Ni squared over Nd. I mean, that's an approximation because we're approximating that on the n side, n is approximately equal to the donor density. But you've seen from your previous homework that as long as Nb is, you know, 10 times Ni, that's a pretty good approximation. And we're going to approximate the same thing. Np0 is equal to Ni squared over Na, which you know from the quiz too. Which it's again, pretty much everyone seemed to get that part. Okay, so now basically we can, you know, rewrite this. I can take the E out, and what I'm going to do is I'm going to put dH, and I'm going to put the NV there. All right, and LH. DE, I'm going to put the A there, and then I'll group the Ni squared over here. Someone suggested that I tap on the screen when I start at the board, and that seems to be working, keeping it in focus. So, but I am trying to keep an eye on it to make sure we don't run into the problem we had last time. All right, so all I've done is I plugged in here, so no big deal. Now, now we use our friend, our best friend, right? Because Ni squared is Np, always, right? And what is N? Okay, our best friend in the world. N is Nc times e to the EC minus EF over KT. That's N. And P is NV e to the negative EF minus EV over KT, our best friends in the world, N and P. Which you already knew this, you know, because we've gone over it again and again. When you multiply N and P then to get Ni squared, the EFs cancel out. which they must because it's a constant. Ni squared is Nc Nv times e to the negative Ec minus Ev over kT Nc Mv e to the negative E gap over kT. So plugging that into J is equal to E. By the way, up here, I want you to notice something. When you plug in for P and 0, see, that's why it's best to remember this, so you can always come up with this form. Because you see, this is all holes, right? The diffusion length for holes, or diffusion coefficient for holes, the diffusion length for holes, and P and 0, the equilibrium hole concentration, same thing for electrons here. When you plug in, like for P and 0, that puts ND there. And so sometimes it confuses students a little bit because it's like, oh, okay, that's ND, that's from the electron side. But you see how it happened. And so if you remember this, and it's best to remember this whole sequence, you don't get confused about how those things mix together. So dH over ND LH plus DE over NA LE, and now let's plug in Ni squared. NC NV e to the negative E gap over KT times E to the EVF over KT minus 1. Okay, so what I've done is I sort of taken this, which again you can remember from your picture, and plugged in to show you something, that the current goes as e to the minus e gap. And in fact, very importantly, if I distribute that, okay, so that's that part. NC, NV, the equivalent density of states. And now I'm going to distribute that in there. And watch what I'm doing here. E gap minus EVF over KT minus e to the minus E gap over KT. All right. Now, this is a good thing to see, because what you see is that the current is the difference between either of the two things, right? And of course you see that if VF equals 0, that's the same as that, and so it's something when it's the same thing in 0. But the point is that what I want you to be aware of is that E gap is always bigger than EVF. And you can see that from, okay, drawing it, right? This is E gap. Now remember, EVF, so this is at 0 bias, and this is VF. Colored chalk. I don't have colored chalk. I should get. Let me make that dashed. Okay. So dashed. So solid. is VF equals 0, and dashed, I gotta make a dash, is VF greater than 0, forward bias. This then is EVF, right? And so as EVF, the band bending goes down. But what you can kind of see is that if EVF exceeded the gap, the barrier would go away, and there would be no barrier whatsoever for holes or electrons, and the diode would burn up. So, you know, this is always true, right? Because in normal operation, if EVF exceeded the gap, then, I mean, this would, you know, it just, nothing would make sense anymore, and you'd have so much current that it would just blow up. That's that. Now, let's proceed and write down I. Well, first let's do J. So if for J, for EVF is much bigger than KT. Now, if EVF is much bigger than KT, right, then this becomes much smaller than that. So it's e to the much smaller a number, and so basically this becomes much larger than that. I mean, the other way to see it is back here. If EVF is much bigger than KT, then this becomes much bigger than 1, and we can ignore the 1. Now, by the way, when does that happen? Well, so that would happen when the voltage was much bigger than 0.026 volts at 300 Kelvin. So those of you that have played with diodes in the laboratory realize that you usually forward bias it to like a half volt or something like that. And so, you know, in normal use, when you forward bias a diode, this is true. The EVF is much bigger than KT, at room temperature anyway. You would have to go to some very high temperature for it not to be true. All right, and so then if that's true, we can ignore this one, and so this becomes EGH T. And we just have the first one. So, you know, that's basically the approximation when, you know, I mean, this would be KT, 0.026. So out here somewhere. Now, I want you to observe something, which is that, okay, look at the equation here. Now remember, this part, can't draw, this part is greater than 0 always, because that's always true. So this is always e to the minus a number. Now, since it's always e to the minus a number, when temperature gets smaller, okay, let's do it the other way. When temperature gets bigger, right, that's e to the minus a smaller number. So if temperature goes up, J goes up. Right, think about it. As temperature gets smaller, that's e to the minus a bigger number. I mean, keep doing it backwards. As temperature goes up, that's e to the minus a smaller number, and e to the minus a smaller number is a bigger number. Now, of course, that makes perfect sense, because the whole thing here is based upon, you know, this happening, and obviously that happens more if there's more thermal energy. So current goes up. Now, you'll see then why. Okay, so let me just draw it here. So basically, if I drew, you know, J versus V, this would be increasing temperature. Because, right, for a given voltage, the current went up. And that's why I did this, because a lot of textbooks, you know, they might kind of, I don't know, stop here or you know, just include this part. You see, if you just included this part, you wouldn't see that, because as temperature, this is a positive number, and you would think, okay, as temperature goes up, that's e to the positive, a smaller number, and so that means current would go down, and that, of course, is wrong. All right, so you have to get it to this form to understand that as temperature goes up, current goes up. And so the plots look like this. All right. Okay. There's one more thing, an aside. So let me erase this part of the board, because we have everything we need over here. Now, I debate how much I want to, yeah, we're in focus. I debate how much I want to belabor the next point in terms of trying to explain it. And as you sort of observe, I kind of like, you know, not worrying about things too much. And you'll note that, okay, we've derived this formula for forward bias, right? Okay. Okay, J for minus VF, or J, I just, you know, J for reverse bias. Okay, what is, okay, now let's, okay, so, and certain textbooks might actually start deriving this, okay? And be like, oh, okay, we need to derive what it is. Well, okay, the thing is that the answer is the same. I'm running out of room. I mean, it's the same thing, okay? Just this over here. Meaning, Gretz, get away from there. Meaning that the, by the way, you may be interested. This is my cat, Gretz. And he's okay, but he likes biting the tripod of the camera. Getting back to this, the point is that if you plug in minus V, all right, the formula works. And so, okay, if we do everything, V, okay, now I'll write it as VF because reverse bias would be minus VF. Of course, it goes through 0, right? And it's sort of hard to draw because, you know, I mean, this isn't really the way it looks because it's a, you know, it's an exponential. It really takes off. But you see that, just going over to here, because it's the same formula, that as VF becomes negative, right, okay, this becomes e to the minus a larger number. And so eventually, this becomes a constant where that value is E dH over ND LH plus DE over NA LE NC NV E. Okay, remember this for reverse bias, negative VF, right? That, you know, that can exceed D gap because that's basically reverse bias is going the other way, right? It's making the barrier even larger. So in reverse bias, that can become e to the minus a really big number. And so e to the minus a really big number is 0. Okay, so, all I have to do here is write e to the minus e gap over kt. Because this one went away. So this constant value out here at a far enough reverse bias is just that. And the point is that even though we derive this formula for a positive forward bias, it works for negative as well. And so it's the same formula. And some texts kind of belabor that a little bit, but there's really no reason to. And since it is the same equation, it connects properly. And of course, again, at BF equals 0 is 0 because that minus that is 0. Okay, and the last thing we're going to do, so first of all, let me draw I. Okay, so I is J times A. And so that's, I'm going to write as I naught times where I naught is all this part times A, the area. I don't think I used A anywhere else. And the point is that, okay, if you move far enough away, okay, it's approximately equal to I naught e to the minus e gap minus EV over KT. Because we could ignore that part there. Now, we're going to do solar cells, but just very briefly, what we might do is that if we get to the end of the course, we can come back and go back into solar cells if you want. Now, we can refer to this diagram here because. Remember, and I'll get rid of the reverse bias here. Remember, when we forward bias it, we get electrons and holes. And that constitutes our current, which I'm going to start referring to as dark current. Now, if I shine light on my diode, what's going to happen is that I'm going to if I have sufficient photon energy, I'm going to absorb the light photon and move an electron to the conduction band. Basically, a photon comes in, it hits an electron in the valence band, kicking it up to the conduction band. And we can talk more about, the photon energy having to exceed the band gap and stuff like that. And it creates what's called an electron-hole pair. Now, you can see what's going to happen here, which is that electron is perched up there, and so he sees this, lower energy over here, so he's going to go that way. And the same thing for the holes, he's going to go that way because holes float, remember? And so if you look at this, okay, that electron going that creates a current in the opposite direction. And so this is in the dark, and in the light, all we do, okay, because if you think about it, okay, if I shine light on and I create electron hole pairs, because the barrier now is an anti-barrier to the movement of these generated electron hole pairs, because holes want to go that way and electrons want to go that way, the the amount of current you get from the light is independent of voltage. So all I do is I subtract a component IL. So, you know, solar cells, I mean, in terms of just understanding basically what happens, is pretty easy. I mean, you shine light on it, and you basically get a current component in the opposite direction, in the negative direction of the dark current. Again, we might come back. We'll see the timing of things, but what I want you to remember, okay, for those of you that have had some discussion of solar cells before, you will realize that the maximum power is here, because power is current times voltage, and with increasing temperature, right, the same thing's going to happen. As temperature increases, that's going to go that way, and so the maximum power point will get smaller. So because of all this and how it works, as the temperature increases, solar panels produce less power. And so you can see that directly here from the equations. And that's all we're going to do about solar cells. Again, we may come back to it, but you can understand simply now, because you understand the semiconductor physics of it all, that when you shine light on it, all you do is you add a negative current component that's independent of voltage. Now, by the way, saying it's independent of voltage, well, if you go to high enough voltage, right, the barrier becomes so small. And remember, the barrier is an anti-barrier for these what's called photogenerated carriers, because, you know, electrons like to go that way down the hill. So as you go to a high enough forward bias voltage, you can cause IL to go. So IL, as you get closer here, can go down a little bit. And you know, that's one of the things you wrestle with when you design solar cells, because you don't want that to happen, of course. But maybe we'll talk about solar cells a little bit more later in the course. If we do, it would be to connect in the semiconductor physics with, you know, how you actually use them and determine the power levels and things like that. So for now, I'm going to erase this. And we have one thing left to do with diodes. Actually, there are more things that need to be done with diodes. We've derived this, you know, just using diffusion theory. There are other potential current components for a diode, particularly recombination. And again, I've chosen for this course that as you know, we're going to do bipolar transistors next, and then we're going to do MOSFETs, and that sort of completes the basic understanding of semiconductor physics and devices. And then maybe we might circle around and talk about recombination current. But for now, I don't want you to worry about it. Just keep this picture in mind here, in this equation for J. Now, finally, there's one more thing we have to do, which is we have to understand, and this is because the next thing we're going to do is bipolar transistors. We have to understand that a p-n junction can be, I'll call asymmetric in its current components. And you can see that directly from the equation, which is that, okay, this is the, let me erase my light here. This is the hole component, and this is the electron component, right? You see them in the equation. And so this component represents the holes flooding over from the p side to the n side. And this represents the electrons flooding over from the n side to the p side. So we can draw a little diagram here. Okay. And so this is p, and this is n. Let's forward bias it. Remember your mnemonic. Forward bias is a positive voltage on the p side. This is ground, 0 volts. I mean, I don't know if I need to explain that. But anyway, let's consider the case, and I'll do it pictorially, where the p side is doped much smaller than the n side. Okay, so I'm indicating with the big ND that the n side is really more heavily doped than the p side. All right, now look what happens. Okay, if ND is much bigger than NA, the whole component is small. But Na is much smaller, and it's a denominator, so the electron component is huge. There's holes and electrons. Now, of course, that makes perfect sense, because if you have more doping on the inside, it makes sense that you're going to get more electron current, right? So you don't really almost need to refer to the equations to understand this. You can just sort of reason it out. There's more electrons to start with over here. So when you forward bias it, you're going to get a more electron flow than hole flow. So this is where I'm going to end this lecture, because we have to understand this principle in order to do the next device, which sort of flows from PN diodes, which is the bipolar transistor. So I'm not going to get started on a bipolar transistor today, but I want you to remember this picture that comes directly from the equation, and also just reasoning that if I dope one side lower than the other, I can get an asymmetric distribution of hole and electron flow in my total current. Okay, so remember that for the next lecture, which will be on bipolar transistors. And I don't think it went out of focus once. So the person that told me that trick, it appears to have worked. Okay, thank you.